No
Yeah,
worries.
great pleasure to have Gourab Rai from University of Victoria. Yeah, he'll be telling us about universality of dimers via imaginary geometry. So all yours, Gaurav. Yeah.
Thank you very much for this invitation. I would have loved to be there, but unfortunately, I have to keep the talk online. So this is kind of a long project, still going with Nathaniel Berestiki, who is currently in Vienna, and Benoit Lerrier, who's in Paris. Um, and it all started when when I was a postdoc in Cambridge. Okay, so this talk. So here's the plan. So in the first lecture, I'm going to give sort of a leisurely introduction to what the model is and where it stands in this whole area of statistical mechanics. And then I'll talk about the perspective that we took in order to understand this model. Um, what we want to understand in this project is to get some universality picture of scaling limits of dimer models. Um, and the new perspective that we took is to exploit the connection with spanning trees and the recent development of Schramm loaner evolution in order to get conformally invariant scaling limits. So that's the perspective that we took. Now there's a big group of people who work on dimer models, uh, and the basic approach before our work was to use the algebraic side. So however, when I started this work, I was not a dimer person at all. I was working extensively on spanning trees, and that's how I kind of got into this project. So if you are familiar with a typical dimer talk or lecture, this is not going to be like that. Very soon, we're going to be talking about spanning trees and probability theory. Okay, so uh, so the whole story, you can also maybe think of understanding spanning trees better with the dimer model in the back of our mind. Okay. So in the first lecture, I'll give you some overview of the results and some of the future directions that we can take. And in the second lecture, I'll give a sort of a detailed outline of the proofs of one of the typical applications of our main theorem. Okay. All right. So by the way, feel free to interrupt me anytime you want and ask me questions. Um, so what is the dimer model? Well, it's a model of perfect matching. So we have a bipartite graph, okay, and we'll be working with planar graphs in this talk. And what is the model? Well, we are going to match. We're going to look for perfect matchings. So imagine you have the bipartite graph with some black and white vertices, and what we want to and we are going to uniformly pick a perfect matching. So what is a perfect matching? Well, every white vertex is matched to exactly one black vertex, and we look at the collection of all such matchings and pick uniformly one of them, and we want to understand how this looks. Um, the thing that we are going to want to focus on is we are going to take a graph of very small mesh size and try to understand the scaling limit of this model in some sense. Okay. So as you can see, there's a lot of constraint on the graph for even a matching to exist. But throughout these two lectures, we are going to simply assume that it does exist. Okay. Um, so okay, so this is kind of what I said. Um, a slight variation you can look for is you can add weights to edges. Okay, so you can think of a graph with a certain weights attached to every edge, and the probability of picking a dimer is proportional to the product of the weights of the edges which the dimer occupies. Okay, and so this gives us a probability on measure on perfect matchings. Okay, and as I said, we'll mostly talk about the planar bipartite case. All right. Okay. Any questions about the definition of the model so far? Um, if not, let's continue. So I'm going to give you some pictures Um, by the way, I'm not monitoring the chat, so maybe open it on the side. Okay, so I'm going to show you some picture just for some
No, that's
visual.
okay. If there are any chats, I'll interrupt you. And
Okay, thank you. Um, so these pictures, we're not really going to talk about these models in details of the pictures I'm going to show you, because this is a universality. I mean, our graphs are going to be any sequence of graphs satisfying some general properties. But maybe some visual pleasure, let's look at some of the pictures which are usually shown at the beginning of a dimer talk, especially if it's on some regular lattices. So if you take the dimer on the square lattice, for example, you can think of it equivalently like a domino tiling. Okay, so this picture from this picture, you can easily see what the connection is. So this is on the left hand side, we have a perfect matching of a square lattice, and on the right hand side, I've kind of thickened every dimer into a domino like this, and this gives us a perfect tiling of this square. Okay, so on the square lattice, one equivalent way of thinking about perfect matching is try to understand a uniform domino tiling. Okay. If you change the lattice to the hexagonal lattice, you can also have a similar picture. So what we have in the hexagonal lattice, we have three types of edges in three directions like this. So what you can do if you want a tiling picture is you can take three different types of lozenges. So one for each direction. So lozenges are basically rhombi, but with three different orientations. And for every perfect matching on the left hand side, on the right hand side, you're going to get a tiling with these lozenges. Okay. So in a sense, dimers on the hexagonal lattice is equivalent to a uniform lozenge tilings. Okay, so um, we're going to come back to the hexagonal lattice in a minute, but before that, let me give you maybe a bit of history. So this, has been studied for a long time. It's one of a very most, it's a very popular model in statistical mechanics. People like Kenyan sort of maybe started this whole journey, and then probably Okunkov, Sheffield, and Dubeda, de Tillier all produced a fantastic series of works. Um, and the thing I want to point out in all these works is that um, uh, it usually starts with studying something called the Castellan matrix, or maybe some variant of that. Okay, um, so this gives us the connection to the algebraic side of this story. So what happens is that if you have a graph, you have the adjacency matrix, and what you can do is you can put some signs on the edges of this adjacency matrix, and by some magical connection, it turns out that if you put the signs in a clever way, then the dimer partition function exactly becomes the determinant of this Castellan matrix. Okay. So this kind of opens the door for a lot of analysis. For example, if you want to understand, well, if you pick two edges and you want to understand, well, what is the probability that a dimer is in edge E1 and that another dimer is in edge E2, well, you can look at the Castellan matrix of the dimer without the rows and the column corresponding to those edges. This relates you to determinants. This relates you to the inverse of the Castellan matrix. So basically, if you can understand the inverse of the Castellan matrix or the Castellan matrix very well, then you can understand anything that there is to know about the dimer model. Okay. Okay, so this is the exact solvable side of this model, and you can get remarkably exact results. So for example, if you take the m by n torus, for example, then if you want to compute the partition function, you get this exact formula. Okay. Um, you may notice that this cosines is somewhat related to the eigenfunctions of the Laplacian on the square, and there is a good reason for that. The determinants of the inverse of the Castellan matrix is somehow related to the Laplacian inverse on the graph. Okay, so more about that later in what's coming. Okay. Okay, so what is the question that we are going to ask? What we're going to do is we are going to encode the dimer model on planar bipartite graphs by height functions. Okay, so we're not going to ask questions like what is the scaling limit of a dimer being in some edge and dimer being in the another edge as you rescale the graphs uh, to have smaller and smaller mesh size. We're going to ask about a slightly more global observable, which is this height function. So I'm going to give a precise definition of height functions in a few minutes, but before that, here is a visual picture of what a height function um, uh, is for the hexagonal lattice. Okay, so this visual picture is not always possible to sort of draw the height function by looking at the dimers like immediately, but you can actually do it for the hexagonal lattice. So that's why I kind of wanted to show you this picture. So what happens is that if you look at the lozenge tiling side of of this dimer tiling, then if you look at it correctly, you'll see that these lozenges kind of form a stack of cubes. Okay, so this, for example, is a cube. Okay, and well, what is the height function? Well, the height function is going to be so you can imagine this is the floor. So the height function is going to be simply the height from the floor. Okay, um, I'm going to again give a precise definition in a minute, but this is the visual side of this story. So as you can imagine, that there is a function from this box to R for every dimer tiling of this piece of the hexagonal lattice. Okay, and what you can ask, well, you can, the question we'll be asking is, if you pick a big hexagon and think of the lozenges being very, very small, then what happens to the height function? Okay, um, something, so some question like that. All right. So okay, so this is the definition for the hexagonal lattice, but let me give you a way to define height function in sort of general bipartite planar graphs. Okay, um, so it is going to be a function from so it's a planar graph, so there are some faces. So it's going to be a function from the faces of the graph to R. Okay, and it is going to be defined through its gradient. Okay, so what I'm going to do is I'm going to tell you, given a dimer configuration, a function on the gradient of the faces. So if you have some face like this and some face like that, I'm going to tell you what is the difference in the height along those edges and tell you how to think about that. So in particular, I want to give you a function, an antisymmetric function on the edges of the dual graph. So maybe let me draw some face here. I want to define an antisymmetric function on the dual graph. Okay, so if V and U are faces, such that if you go along any cycle, the height differences add up to 0. Okay, so how to do that? Well, I'm going to define two functions, one for the dimer and another kind of out of the blue, such that it's going to be antisymmetric. And if you count the amount of mass going out of the black vertex, that's going to be 1, and the amount of mass coming into a white vertex, that's going to be also 1. Okay, and then what I'm going to do is I'm going to subtract the two. Okay, so more details on that here in the next slide. So um, so first I'm going to define something called a dimer flow. Okay, and this flow is going to be a function of the dimer model. Okay, so if you have an oriented edge, okay, you can define um, the dimer flow is an antisymmetric function on the edges. So you define it to be 1 if the dimer is present, and you define it. So if you go from the black to a white vertex, so if E minus is black and maybe let me draw this thing. So if E minus is black and E plus is white, you So the dimer flow is flowing a mass 1 out of the black vertex into the white vertex. Okay. So you define it to be 1 if the dimer is present and 0 otherwise. Okay. Now it's clear why this is uh, so it's clear that why it satisfies the properties which I just mentioned. If you have a black vertex, the total mass going out of a black vertex is 1 because there is exactly one dimer attached to a black vertex. And similarly, for a white vertex, there is exactly one dimer attached to a white vertex. So the mass going into a white vertex is also 1. Okay. Um, okay, so that's an antisymmetric function on the edges. But then I'm going to take sort of any function on the oriented edges of my dual graph, such that which satisfies the same properties, that the mass out of a black vertex is 1 and into a white vertex is 1. Okay. um, so this function is called the reference flow. Okay. So um, this is called the reference flow, and it's going to be important later. We're going to choose our reference flow depending on the geometry of the graph later on. Okay. So um, at the moment, it could be any function that you can think of satisfying these properties. For example, if it's the square lattice, what you can do is you can uh, define a mass 1/4 going out of each edge assigned to adjacent to a black vertex, and this defines for us the reference flow, because for any white vertex, the mass coming in is also 1, and the mass going out of a black vertex is also 1. Okay. So then we take the difference of these two reference flows. And if we do that, then we see that the mass, since we took the difference, mass out of a black vertex is 0, and the mass into a white vertex is also 0. And so therefore, this defines for us a function such that if you look at any cycle formed by phases, the total mass going the total amount of flow for this delta as you go along the cycle is 0. Okay. So this is enough to define a function on the faces, well, up to a global shift of r, but you fix one of the faces to be 0, and this defines for us the function, which is going to be at the moment a function of the dimers and a function of the reference flow. Okay. Any questions about this definition, because it's going to be important in what's coming.
This can be defined with added weights also, right?
Yes, so the added weights on the graph will be useful for the probability measure on the dimer, but this is a completely deterministic statement. Given any dimer configuration, I can assign a function from the faces to R. There is no probability yet.
Okay, thank you.
Right. Okay, so this defines for us a function on the faces. Okay, and this is kind of in bijection with the dimers. Well, I'm saying kind of because you need this reference flow, and also there's this modulo r. But you can see that you can understand at least at the discrete level anything you need from about the dimers from this height function. Okay, it is this height function that we are going to study now. Okay. um, so uh, uh, and one nice thing is that it's now really a function which you can maybe plot and think about, rather than looking at a bunch of matchings on the edges. So one thing that you can ask, well, if you look at a sequence of squares growing to the square lattice, for example, can you get, for example, a Gibbs measure of this height function, or in any lattice or in any sequence of graphs? Okay, so these kind of questions you can definitely start to ask. We are not going to talk about the infinite volume limits uh, in this particular talk, but let me mention one fact which might tell you why um, looking at the scaling limit is probably something the right thing to do, is that if you take a sequence of height function corresponding to the domino tiling picture which I presented, then with, let's say, zero boundary value on one of the boundary faces, then the height is there all is going to blow up. Okay, so so here there is no subsequential limit you can talk about, because the height function can take value in a non-compact space R. So if you make the things bigger and bigger, squares bigger and bigger, the height is in fact, and I'll tell you why that's the case, it's going to fluctuate wildly, and in fact there is no infinite limit gives measures, at least on the square lattice. Okay, so so in that sense it's a little bit wild thing to study, um, and it's related to the Gaussian free field, which I'm going to define next. Okay, okay, so this talk is also going to talk about dimers on multiply connected domains. So what can you do on there? Well, you can define this antisymmetric function whose flow around a cycle, any contractible cycle, is zero in the same way. However, that will not correspond to a function because, for example, on torus, let's say, if like here I have a picture, if you go along a non-contractible cycle, just having a zero flow, a zero circulation along a contractible cycle is not enough to give us a function on the faces. So, but with a little bit of abstract theory, which is basically a discrete version of Hodge decomposition, what you can get is that you can write down um, uh, this zero circulation antisymmetric H function, or one form, as the gradient of some function which is on the faces, plus another one form which is nice in the sense that this one form is basically the same as a finite collection of numbers which depends on the topology. Okay, so if you have a dimer on a multiply connected domains, I'm going to give you more clear definitions on and how to handle them in what's coming. But there you have two things to handle. One is a function um, on the faces, which is going to correspond to the Gaussian free field on the multiply connected domain. Um, and the other thing is going to be a one form. It's not going to be a function. It's going to define remain or defined only on the edges. Um, but it's harmonic. It's some kind of harmonic extension of a finite set of numbers. So let me explain what these numbers are in the torus, for example. So in the torus, um, this this harmonic one form is going to be uniquely defined by two numbers. One number is what you get by looking at a loop which goes along this side of the torus, and another, the number b, is the number that you get by looking along the other side of the torus. Okay, so if you know these two numbers, you can know exactly this harmonic one form, and this comes from some abstract theory, um, some abstract algebraic topological lemma. Okay, so is the definition for how to handle height function on a general surface. I mean, you should have the torus in mind, really, but you can define it generally. For example, a pair of pants, or annulus, or things like that. Sorry, Mohanda, I think you're muted.
Yeah, no, I was just asking whether so there's one topological term corresponding to this H yeah. So there seems to be one topological term corresponding to this H cross.
Yeah, yeah. Sorry, you're getting completely cut off. So I just heard the last part of of your question. So yeah,
Never mind. I'll type it in chat.
Okay, thanks. So maybe just to repeat what I said, this topological term corresponds to this H cross, and you get a function which is analogous to the function in the simply connected case in this first term. So you have one topological term and one actual function on the surface. And this topological term is it's in some sense finite dimensional, because it's completely defined by this a collection of numbers which is actually in bijection with the homology of the surface we're talking about. So in case of the torus, it's completely defined by two numbers, one which is obtained by looking at by adding up this nabla going along a cycle going in the vertical direction, and the other one is what you get by going along a cycle in the horizontal direction. And this is harmonic. So this harmonic one form, one way to think of it is like harmonic extension, in a similar way that you have a harmonic extension of values on the boundary of if you have a certain function on the boundary of a domain, you can harmonically extend it. This harmonic one form is like that. Its divergence at every vertex. I mean, if you sum over all the out sum over all the values of H cross going out of a vertex, that's zero. So it's in harmonic in this sense. It's equal to the average. Um, uh, uh, well, average it's defined on edges, so you have to think of the right thing. And given these two numbers, you can uniquely find one H cross, for example, on the torus, which satisfies this property. Okay, so I hope this part is clear. Um, so what happens in the large scale? Well, what we want to understand is the large scale behavior of the fluctuations, right? So we have H and this mean. Okay. So this is so okay. Now we get to probability. So we are going to pick a dimer uniformly at random, look at its height function, and we're going to subtract the mean. Okay, we are going to look at fluctuations, and now you see this weird reference flow that I defined, or didn't or kind of said that you can take any reference flow that you want. If you subtract the mean, that reference flow is a deterministic object. It didn't depend on the dimer configuration, so therefore it will go away in this expression. Okay, so whatever be the reference flow, this expression, this quantity H bar is a random uh, function, let's say in the simply connected case. Okay, so what we want to understand is how these things, we want to take a sequence of graph with mesh size going to 0, and we are going to ask how to take the scaling limit of this object. Okay, now we immediately run into a whole bunch of problems with boundary conditions, which is something that I didn't really specify yet. So let's so I'm going to mostly stick to the simply connected case because that's kind of the base case. But sometimes I'll just tell you the differences with the multiply connected case as we go along. Okay, so mostly it's going to be about the simply connected case. Okay, um, that's where the key idea lies. So what about boundary conditions? Well, boundary conditions on dimers play kind of a huge role. Unfortunately, well, I don't know if I should call it unfortunately, but it also gives rise to very nice mathematics. But you have to be always careful with the boundary conditions. Okay, so for example, the boundary condition here, in terms of height function, is something kind of nasty. So the height here is kind of maximal possible, and then it goes down, and then it stays on the floor, and then it kind of goes up again, and then reaches the ceiling. Okay, so you have kind of a ceiling here, and so the boundary values are along the ceiling here. Then it comes down to the floor, and then it stays flat along the floor. Okay. Now, why am I saying that this is bad? Well, the boundary values we are going to be mostly interested in is going to all lie on the floor. Okay. Now, what happens now if you have these sort of non-flat boundary conditions? Well, you can say that there are some frozen regions. So, for example, here there is no fluctuations at all. This is a very well studied dimer. This is the model. This is the lozenge tiling on the hexagon. And as it turns out that here it's uh, not always random near the corner. So near the corners there's some well-defined frozen regions like this, and there is some randomness in the middle. Okay, so in this area, the frozen parts are called the frozen, well, they call the frozen region, and the random part is called the liquid region. Okay, um, there's also something called the gaseous region, but we're not going to talk about that. um, so the difference between frozen and the liquid region is that in the liquid region, the correlations are going to decay. Okay, in the dimer, well, by correlation I mean expectation of hx hy. So here it's for example, it's completely the correlation is covariance is kind of one or something. Okay, so this phenomena is called the Arctic Circle phenomena, and it gives rise to very nice mathematics. Um, Various things are known about the fluctuations here in the liquid region. Um, so what we are going to talk about from now on, and the graphs I'm going to define on which we are going to talk about how height functions, will be exclusively in the liquid region. Okay, now how to know if something is liquid or frozen? Well, there is a beautiful paper called Dimers and Amoeba by Kenyon Okunkov and Sheffield, who gives some exact criterion, again based on the Castellan matrix approach, which tells you exactly when is a dimer model in the frozen or when it's in the liquid region. Okay, anyway, so we are not going to talk about complicated boundary conditions um, like that. Our boundary conditions will be such that one can that it is guaranteed that the height function inside is in the liquid region. Okay. Okay, so what's the conjecture? Well, in the liquid region, it's conjectured that the height function converges to a certain um, object called the Gaussian free field. Um, so here's a definition with boundary conditions which I fixed to be zero. So it's again a model of height functions. Now it's continuous, um, and but there is one issue, which is that this is not really a function. Okay, so probably all of you have seen this definition before, but let me still mention. Excuse me. So it's a Gaussian process. So it's defined on all points in a continuous domain. Okay. Um, and the nice thing is that it's conformally invariant. Okay, so for every, you can think of the marginal as being some normal random variable which is conformally invariant. However, we cannot really think of it as a normal random variable because it's a technically it's a normal with infinite variance, but it's not too bad. I mean, what you can do is you can integrate it with any smooth function f, and what you get is an honest normal random variable with mean zero and variance given by um, integrating f with respect to something called the Green's function in the domain. Okay, so well, what is the Green's function? Well, it's so one can define it as a solution of some PDE, but maybe one way to think of it, which will be useful for us, is that it's defined as the expected local time a Brownian motion spends. So it's a function from d cross d to r. So if you look at GD at x comma y, it's the expected time a Brownian motion spends at y started from x. Um, Right. So what is the difference between random height function and the DGFF? Well, first of all, it's not Gaussian, so it's something which is defined through the dimer, but there's no reason for it to be Gaussian. Uh, However, in the scaling limit, the conjecture is that as soon as you're in the liquid region, they both kind of converge to this continuous Gaussian free field. So you can think of this as a version of um, a central limit theorem, but in two dimensions. Yeah.
I had a small question too about this Arctic circle phenomenon. Sorry.
Uh-huh. In the before maybe.
So
Yeah.
yeah, why is the so here it seems that the liquid region it, it occupies most of the space inside this hexagon, right? So if we keep
Mhm.
increasing the size of my hexagon, then will the same behavior persist? Is it mostly going to occupy? Is most of the thing going to be a liquid region?
Right. So I guess the question is how you're making things big. So one way of thinking of making things big is you kind of fix this hexagon, but sort of make these lozenges very, very small. Okay. So that's like taking a big thing, but sort of squishing it down into maybe a 1 by 1 hexagon. Okay.
Right.
That's
Yeah.
that's taking the scaling limit. And if you take the scaling limit, you're going to get actually a perfect circle here, and inside you're going to get a function of the a deterministic functional of the Gaussian free field. It's not exactly the Gaussian free field, but slight variant of that. But this picture will sort of get to a continuum picture once you take the scaling limit. On the other hand, you can ask, well, what if I just zoom into the picture? Well, there has been studies of that as well. So if you zoom into here, you're going to get, I mean, there's some very nice math related to all of this. You're going to see all these steps sort of everywhere. And these things can be sort of studied very explicitly using random walks condition to avoid each other and things like that. So you should look into the works of Iwan Corvin if you're interested in like that. And also Amal Mojumdar is doing some fantastic work in this direction. So since this is a nice lattice and you have all this Castellan theory at hand, you can actually do very explicit computations for this particular model.
Okay. Thanks.
Yeah. Can we consider this model on the sphere so that there is no boundary condition? Yes, exactly. So you can consider this model on the sphere without boundary condition. One thing people like to do is talk about or the torus, and one reason is that um, there's some nice mathematics going on with because you can think of the lift of the torus very nicely. You can lift the torus in a very nice way into the whole plane, but certainly you can think of it in the sphere. And if you set up your graphs in the correct way, it should behave in the same way as in the simply connected case, which I'm going to describe in more details in what's coming. Yeah. Okay. Any other question? Okay. So that's the Gaussian free field. Um, so as Mahan asked, well, what's the difference between the discrete Gaussian free field? Well, proving that the discrete Gaussian free field scales to a continuous Gaussian free field is much easier than answering this question. And the reason is similar to the fact that proving the central limit theorem or convergence to Brownian motion for some of IID Gaussian is probably it's much easier than proving it for any general sequence of IID random variables. Okay. So you kind of need to study these things. And for various simpler models, like for example, homomorphisms of the 6-vertex models, they're also supposed to converge to the Gaussian free field, but they're not known. Okay. So, okay, so we're also going to consider a slight variant of this zero boundary Gaussian free field. So here, one thing I did not maybe mention is that this Green's function is, so I said you look at the expected local time of Brownian motion. But you look at the Brownian motion and you kill it when you hit the boundary. Okay, so that's the Brownian motion we're looking at. There are other variants of the Gaussian free field as well, but we're only going to stick to the Dirichlet boundary conditions. Okay. Okay, so there's going to be a slight variant of the Gaussian free field we're going to consider. There's going to be some boundary condition. So you can think of some function defined on the boundary of T, and we're going to talk about the Gaussian free field, which is the zero boundary Gaussian free field plus the harmonic extension of this function we defined on the boundary. So there is a unique harmonic extension of any function, well, any reasonable function defined on the boundary. And when I say GFF with a boundary condition determined by something, I mean this. Okay. Okay, and now the start of this project is at the following point. So if you want to find the asymptotics of the Castellan matrix, um, if you do not have nice graphs like the lozenges or the square lattice, then it kind of gets hard. Well, well, because of the fact that if you look at the Castellan matrix, it's like the derivative of the Green's function. So you kind of need good behavior of the derivative of the Green's function at very, very microscopic level. And you kind of hope that even at the discrete level, things are, I mean, these functions are sort of analytic, meaning that they kind of, even at the microscopic level, satisfy certain Cauchy-Riemann equations. Okay, but this is a lot to ask if you don't have, you know, a lot of information about microscopic regularities of the graph. I mean, one thing maybe to keep in mind is that if you, for example, take the square lattice and you perturb it slightly, okay, um, maybe even randomly. Okay, so maybe you take a random environment, okay, on the square lattice where the environment is nice enough so that still, for example, random walk behaves in the same way as in the square lattice. For example, random walk still converges to Brownian motions. Okay, so take, for example, a uniformly elliptic random environment. So in that case, the Castellan theory is kind of hard to do because you do not have, I mean, this extra randomness creates enough irregularity so that it's hard to do, make sure that the calculations go through. So what we want to do is to sort of, that's why we wanted to get out of this Castellan approach in order to show the universality. Okay, so for the square lattice, it was shown by Kenyon that there is a Gaussian free field scaling limit, and later it was extended to some class of graphs called isoradial graphs. Again, these are nice graphs which are amenable to discrete complex analysis. And there is a lot of works by Bukpetov, Korin, Petrov on laws and stylings as well. Okay. Now, what are our assumptions on graphs? Our graphs are not going to be square lattice or the hexagonal lattice. It's going to be a sequence of graphs satisfying basically a couple of assumptions. One assumption is that we want invariance principle to hold. So we want random walk to converge to Brownian motion, and there is a very good reason to assume this because of certain connections to spanning trees, which I'm going to explain in a minute. Now, what does this mean? It means that we're basically assuming that if you have any discrete harmonic function on your graph, if you rescale your graph, it converges to some continuous harmonic function. This is more or less the same thing. Um, and the difference from the Castellan approach is that there you needed to assume that you needed to go one level further. You needed the derivative of the discrete harmonic function to of a discrete harmonic function to converge to a derivative of a continuous harmonic function. So you needed much more regularity in the Castellan approach. Okay. Um, by the way, should I take some break at some point? I'm not sure now until how much I should speak.
As you please. You can, yeah, you can carry on till let's see. So it's, yeah, for it's a 1.5 hours. So as you please. If you want to give a break for a couple of minutes in the middle, that's fine. Up to you.
Okay, yeah, okay, so yeah, so if all of you want to break, please let me know. We can also decide together if you want. Okay, so I can continue for now. So so unfortunately, if just using the fact that the random walk converges to Brownian motion is not going to be enough. Now, why? Because here one difference from the central limit theorem in one dimension is that we are not rescaling this quantity. So if you remember in one dimension, the central limit theorem, well, we had this x1 plus up to xn. Well, okay, so you subtract the mean, okay, and then you divide by square root n times the variance. Okay, okay, so in the square root of that, something like that. So you rescaled by this square root n. However, here you do not need the rescaling. Okay, that's the kind of one difficulty, or one thing which kind of makes things a bit harder. So that's why if you just know random walk converges to Brownian motion, it should in principle be enough, but you somehow also need to control in a certain sense what happens. You need some control on the microscopic structure. So we wanted some control which is not going through discrete complex analysis. So we opted for the next best thing, which is, so okay, so this means that we kind of need to and okay, so let me not say about the mean at the moment, but the next best thing is to assume something very natural, which is an which is a Russo-Seymour-Welch assumption. Okay, so this whole Russo-Seymour-Welch theory, you may have heard of this in percolation, and it's one of the key ideas which from the works of from Hugo and Vincent Tassion. It's one of the key input or key thing that you need to prove in a two-dimensional model in order to understand very well. First of all, you understand anything away from criticality very well, and at criticality, it's kind of one of the key things that one needs to prove. And the theory is now so developed that once you know this, you can kind of say a lot. Okay. Now, what's the Russo-Seymour-Welch for us? There's no percolation, but we kind of need the analogous thing, which is the following: that if you take a large enough rectangle, large in the microscopic sense. So imagine you have a graph with mesh delta, and you have a small number delta naught, and which is fixed forever. And what you want is, if you have a rectangle which is 3 by delta naught times 1 by delta naught size, so it's a big rectangle, but the mesh size is still delta. So your graph is kind of has mesh size delta inside. What we want is that if you put the rectangle anywhere, probability of crossing the rectangle for a simple random walk, starting from anywhere in a reasonable place, without exiting the rectangle, is uniformly positive. So there is a C and a delta naught such that this probability is uniformly positive irrespective of the delta. Okay. So if I was allowed to take my delta naught huge, okay, in particular, if I could take delta naught something like delta, then this would be a consequence of the invariance principle, because I already know that the random walk is very close to a Brownian motion at macroscopic scales. Therefore, and for Brownian motion, this is very well known that you can cross the rectangle with some uniform probability. You can use conformal invariance for that, for example. However, this kind of tells you there is some uniformity on the behavior of the random walk, um, even at some large but microscopic scales. Okay. Now, um, for example, the example, for example, of the random environment which is uniformly elliptic, in that case, one can prove this assumption in a quite straightforward manner. Okay, and there are many other graphs where you can prove this. So, for example, one can prove this in a supercritical percolation cluster of bond percolation on Z2. These kind of things can be shown. Well, you're not going to get the delta naught, but you need to take something like log of delta, but that is also somehow should be enough to get the kind of results we're looking for. Okay, so there is some flexibility in this assumption, but it's certainly much easier to check than and holds in a much more generality than discrete complex analysis assumptions. Okay, so is this RSW any questions about this RSW assumption? It's kind of going to be key later. Okay, so right, so we are going to get the universality for a nice collection of graphs, and the reason and the connection we are going to use is between dimers and uniform spanning trees. Okay. So I'm going to explain how to get this connection in a few minutes, and then what we're going to do is we're going to combine this with some scaling results of uniform spanning trees. Okay, this comes from the work of Schramm, and connect this with a recently developed theory of imaginary geometry, which is developed by Miller, Sheffield, and Duveda, to identify the limit. Okay, so this kind of a lot of information in this slide. It's kind of the broad outline of what's coming, and kind of the goal of the next part of the remaining time in this particular talk is to explain how these stories kind of fit together. Okay. Okay, so maybe it's a good time to take maybe a couple minutes break because I'm going to start talking about the connection with spanning trees right about now. Okay, and then go from there.
Sure.
Okay, so maybe
Yeah,
just
you can start. Yeah.
okay, maybe I'll just continue. So right, so what is a uniform spanning tree? It's a much easier object to understand than the height function. So what we have is you take a tree which spans over all the vertices of a graph. Okay, so that's a spanning tree, and you want to pick uniformly at random from your collection of spanning trees. Okay, so that's a uniform spanning tree. Now there are various relations which connect dimers and spanning tree. I picked the simplest one, which is this so-called Temperley-Fisher correspondence, because it's very visual and it's local, so it's very easy to define. However, there are many other connections. For example, one can use these so-called T-graphs, okay, which connects a spanning tree on a certain graph, which looks which is a directed graph. So it's not very natural, maybe from some certain points of views. However, one can get that the exact connection which Temperley-Fisher told about. This was a long time ago. You can generalize it to other models where the Temperley-Fisher correspondence doesn't work in great generality. Okay. So what is this correspondence? Well, we start with a graph, which is this black graph, okay, and then we add upon it a dual graph, which is this blue graph, and think of this ring that I drew as a single vertex. Okay, so this dual graph is kind of wired here. Okay, now so we have a graph, a black graph and a dual graph. Okay, now on a vertex, so where is the dimer defined? So for every edge um, where a black edge is crossed by a blue edge, I'm going to throw in a white vertex. Okay, so this defines for me a bipartite graph. Um, and for a certain reason, which I'm going to explain later, which is basically topological reason, we're going to remove one black vertex from the boundary. Okay, and this is where my dimer is going to be defined. So this G is this union of these graphs with the white vertices without one of these black vertices removed, without one of these boundary black vertices. Okay, so this graph, as it turns out, has a dimer matching, and um, and then I'm going to tell you how to get to a spanning tree from this dimer matching. Okay, and the connection is extremely simple. So what you do is, if you have a dimer like this, um, you so what but and your black vertex is one of the vertices of this black graph, then you simply extend it. And actually you do the same thing also for the dual graph, but I've drawn it with different colors because it's going to they're going to correspond to two different trees, and one tree will be the dual of the other tree in a certain sense. Okay, to summarize, for every dimer, what we basically do is we extend this. Um, so this dimer, remember, this white vertex was in the middle of an original edge. So we extend this dimer into a complete edge. That's what we do. It's a very local move. Okay, and it turns out that this gives a pair of trees. This blue tree is a tree on the black graph, and this purple tree is a tree on the blue graph. Well, you might ask, well, why is this a tree? Well, remember, there is this outer vertex, which is like this ring, which I called a single vertex. It's like the wired boundary condition. So this orange orange graph is also a tree. Okay, so we have a blue tree and an orange tree. And in fact, the blue tree completely determines the orange tree, because if you have an edge where the blue tree is not present, you'll see that the orange tree is present. Okay, so it's very easy to define, but the only question that you might be asking, well, why is this a tree at the end if you do this local move? Okay, and the reason is completely topological, and it's a consequence of Euler's formula. So let me explain that to you, because it will be useful when we try to extend it to multiply connected surfaces. So imagine you have a cycle like this here, after you do this local move by extending the dimers. Okay, and imagine you have a certain number b of black vertices and a certain number w of white vertices inside this cycle that we made. Okay, we're going to arrive at a contradiction. Now remember that the number of white vertices is the same as, so imagine the portion of the black graph contained in this cycle. Well, for every white vertex there is an edge. Okay, so the number of white vertices basically is the same as the number of edge. And remember that the number of black vertices is the number of vertices plus the number of faces, because the number of black vertices, remember, we had one black vertex for a graph and one blue vertex. Okay, I'm also thinking of this as a black vertex for the dimer. So the number of black is the number of vertices plus the number of faces. Okay, and I'm removing the external face because I'm kind of considering just this graph enclosed by this cycle. Okay. Now, if I apply Euler's formula to this graph, which is this black graph enclosed by this cycle, I'm going to get that the number of V plus number of faces is simply number of black vertices plus 1, and we get this equation. But if we want to have a dimer matching, this quantity must equal this quantity, which can only happen um, which cannot happen, because then we'll have 1 equals 2. Okay, and now if you go back to the original picture, now you see why we needed to remove this extra black vertex, because we didn't want a whole cycle to be present in the original graph as well. This is the reason we removed the black vertex here. Okay, so,
You remove that edge randomly. I mean, what is the?
so we fix this black boundary vertex from the beginning, and we work on dimers on this graph. So it's a non-random thing.
Thanks.
Yeah. So later we are going to take scaling limits. So we're going to have a sequence of these graphs with these boundary conditions with maybe one vertex removed, and these graphs are going to sort of converge to this continuum domain in some sense. So in the end, this thing is not going to matter too much. Yeah, but it has to be from the boundary to make life simpler. Yeah. Okay, so now what happens in a multiply connected domain? Well, we can try to do kind of the same thing. I've kind of drawn two pictures. One is on the torus, and another is as a pair of pans. Okay, now if so, one can try to do the same thing, and if you do the Euler formula calculations, we'll realize where things can go wrong. Okay, we're going to again try to do the same thing. We're going to start with a graph on our surface, um, and we're going to start with a graph on our surface, and then we're going to have a dual graph, something like that, and we're going to put white vertices on the edges, something like that, and we're going to talk about dimer configurations on this graph. And whenever we have a boundary, we might want to sort of create some cycles like this and have a sequence of graph which converge to this manifold in the scaling limit. Okay. Now we immediately run into some problems, because if we apply Euler now to this surface with, let's say, B boundaries and G handles, then we see that well, number of vertices plus faces has to be equal to the number of black vertices, and the number of edges has to be equal to the white vertices. So we need that this quantity must be zero. Okay. Okay, so in the simply connected case, we got rid of of this extra one black vertex to make our life easier. But here we need to do something else. Okay, so there's two cases where we don't need to do anything. One where this is actually zero, and and those two cases are the cases of torus and annulus, right? So G equals to 1, B equals to 0 is the torus, and if B equals to 2, G equals to 0, that's the annulus. Okay. Okay, so I should also write or B equals to 2, G equals to 0. So in these two cases, these exactly match up, and you can take a sequence of graphs without really doing anything, any modification. Okay, but in the other cases, in order to make have a dimer configurations, we need to remove white vertices, particularly on surfaces with negative curvature. Okay. Um, Okay, so we need to remove white vertices, and we exactly know how many to remove. So we're going to remove this many white vertices just to make Euler's formula work. And in terms of scaling limits, we're going to make these punctures sort of macroscopically far apart when we talk about them. Okay. Okay, so now let's focus for a minute on the torus. So on the torus, we don't need to remove anything. But what happens if we try to do this tempered lane bijection, right? So remember, we had this dimer and we extended this into an edge. Okay, now can there be cycles? Well, as it turns out, in the torus, there will be cycles, in fact, but all of the cycles will be non-contractible, must be non-contractible because of this argument right here. Okay? So in particular, there in the torus, the bijection is not with spanning trees, but with a certain spanning forest with a bunch of components where every component contains exactly one cycle. So the graph, sort of in an abstract sense, or maybe a caricature of the drawing, is the following. So you're going to kind of uh, go in this direction and create some cycles, and each of these cycles will be must be non-contractible. Okay. Okay. So so these are what we call the cycle rooted spanning forest. Okay, so on the torus, this is exactly what happens if you do the tempered lane bijection. So here's a simulation of the cycle rooted spanning forest on the torus. Here there is only one green non-contractible cycle, and every other cycle, well, I've not drawn everything, but every other path or branch um, uh, is not a cycle. So there's just one component here. Okay. But in general, the picture could be more complicated. You could have a bunch of cycles like this, and each of these cycles could have a lot of uh, branches attached to them. Okay. And of course, the picture could be even more complicated. The cycles could wind around in two directions as many times as you want. and this is also going to give you a cycle rooted spanning forest. Okay, so this is the simple case where you don't need to remove any additional white vertex. Okay. However, in general, you do need to remove a certain collection of white vertices, and maybe the simplest case is the pair of pans, because in the pair of pans, you have b equals to 3. Um, so this, if you remember this formula, it's 2g plus b minus 2. So if b equals to 3, you need to remove one vertex. Okay, g equals to 0. There's no handle yet. Okay. So we remove this one vertex, one white vertex, and if you remember, one white vertex kind of corresponded to an edge. So you kind of have a picture sort of very locally like this. And what we want, so uh, so now if you ask, well, what is the connection between dimers and these sort of weird forests with cycles on every component? There are cycle rooted forests on this pair of pans which do not correspond to any dimers. For example, if I had a if I tried to if I had a cycle rooted forest, but this is a cycle, and this one sort of went and attached like here, then this is not going to work, because of the same reason that this is going to create a cycle like this, but it's missing one white vertex on the boundary. Okay. So again, because of an Euler formula calculation, you can see that this cycle rooted spanning forest, if the branch sort of connected like this will not correspond to any dimer. So if you want a bijection between dimers and these forest type objects, it's a special subclass of this cycle rooted spanning forest. In particular, what we want, and this is a lemma that we prove, is that from all these punctures, if you look at the branches starting from those punctures, there's a finite number of punctures, 2g plus b minus 2 many punctures. All those branches, after you sample them, must divide your manifold into annuli. Okay, this is an if and only if condition. So the class of cycle rooted spanning forest corresponding to dimers are cycle rooted spanning forest where the branches from each of these, from the two endpoints of a puncture, divide our manifold into annuli. Okay, one can prove that you can always do it, and if it corresponds to a dimer configuration, then this must be the case. Okay. Um, any questions about this? So for example, maybe this picture is probably more visual. So here from the puncture, you could have a picture like this where you have three annuli. One is inside here, one is inside here, and one is outside. So um, and a more discrete picture is here. So here you have one annuli here and one annuli here. And actually, you should think of these edges being already used. So that's why this is also another annuli. Okay. And in general, if you have a bunch of handles and holes, you want this conditioning to be satisfied in your forest. Okay, so what has all this got to do with height functions? Well, here comes an observation by Benjamini back in late 90s. It says the following, that if you want the height difference, then you need to look at something called the winding of the green path. Okay, so if things are embedded on R2, then winding is something. Well, there are various ways to think about it. So, for example, you can look at if things are all, if the edges are all straight lines, you can just go along the edge with no change in winding, and then you just count the angle that it's turned. Then you go along here, then you count the angle that it's turned, and so on. Okay? So that would be the winding of a path. And if you want the height difference between x and y, it's exactly the winding of this green path. So you go along here, turn this angle, go along here, turn this angle, go along here. Okay. This seems completely out of the blue. Why would the winding connect to the height function of dimers? So I'm going to explain to you why this is. Um, so what is winding? Well, one way to think of winding, for a smooth curve at least, okay, is that you look at the derivative of your curve. So you parameterize the curve in some smooth way. you take the derivative of your curve and you look at the argument of this. Okay, so the argument of this is going to change as you go along the curve. So if you integrate this quantity argument of the gamma prime, and you kind of define this argument in a continuous manner, meaning that if you start from here and you change all the way, um, for example, if you start from here and then you change, go all the way here, then you've turned 2 pi. But then you kind of, we do not cut it off at 2 pi. We continue here. It actually turned negative, so it went. Um, uh, Sorry, it started here and it actually became 2 pi actually exactly here, and then it continued. So you went around 2 pi, and you continue adding. So that's what is meant by taking this to be continuous. You continue adding to it. So here it becomes 3 pi, and then it sort of decreased to 5 pi by 2. Okay, so the total winding of this particular curve is 5 pi by 2. Okay. So for example, if you have a curve which is like this, it will have a huge winding, started from here to here, let's say.
Sorry, what was the green path you mentioned earlier?
Yeah, so there is one technical issue that the height functions are defined on faces and the spanning trees are defined on the vertices, right? So one way to think about it is you connect a particular vertex, particular part of the face. You fix some center of the face in some way. In the end, nothing is going to matter because we're going to take scaling limits. But you fix some vertex which corresponds to the dual graph. You go to the nearest, let's say the blue tree vertex, go along the blue tree vertex and connect to the other face. Now, of course, you can ask, well, why did you choose this path? You can also like maybe go here, do something. Okay, so this didn't take us anywhere, but there could be other blue paths connecting like this here. So you could maybe jump to there and go take the other blue path. It will turn out that all of them gives you the same answer. That's kind of the point. Since it's a topological thing, if you close a loop, things add up to 2 pi. So there, at the moment, it seems that there are many potential choices and no apparent connection to dimers. But the magical observation of Benjamini is that there is a one-to-one connection, and I'm going to explain that right now.
All right, thanks.
Hope that's a little bit more clear. It's to make all of this thing come together, you need to work a bit actually. So, but I'm kind of hiding those technical things here. So how
one
to connect?
small thing. Sorry.
Yeah.
So about the well-chosen flow there. So it was right above this slide. So you were computing this winding. I mean, you chose a flow, right? The reference flow omega naught.
Yes.
That defines the height function.
Yes.
So so essentially you're going against it. That is, I mean, your omega is basically directed along the dimer directions, right? I mean,
right.
It's precisely determining the dimer, and omega
Right.
naught has to be, I guess, I don't know. I mean, it has to be against it, so that your winding is exactly computing the height, right? Is that the intuition?
Kind of. Maybe the definition will make it a little bit clear. The point is
Okay.
that but your intuition is I would say it's on the right direction. If you go along the spanning tree path, you're kind of going along this dimer, so you never cross a dimer if you think about that. So that's why it's only the reference flow which is going to matter if you want to compute the height function, but you go along a spanning tree path. Right. So
Okay.
let me give a precise definition of what the reference flow is. So what one can do, so for us, the edges might not even be straight lines. So it could be some weird curved edges like this, but we assume that they're at least smooth in the microscopic sense. And okay, so if you have some piecewise smooth curve, you can extend this definition by adding the winding along the smooth parts and turning the corners. Okay, so I hope this is clear what this means. So the reference flow from black to white is going to be the winding of this red curve. So you go along, start from X. So you start from the face which is to the left of the edge going from black to white. Okay, you go and hit the black vertex and you go to y. So this is the winding of this red curve gamma. Okay, but you subtract pi. Okay? Why do we subtract pi? The way to think of this is we kind of turn the 180-degree angle right here. Okay, and now if you think about it this way, then it's clear that if you add up all the flows out from a black vertex, then you're exactly turning around um, this these red edges like this, and so it's going to sum up to minus 2 pi. Okay, so that's why if you divide by 2 pi, well, the flow out of a black vertex is going to be minus 1. Okay, and another the thing that you can check easily, well, it needs some checking, is that this also defines um, uh, a right reference flow from the white vertex, in the sense that flow out is going to be 1. Okay, it's not the same proof, but it's for the same reason. Okay, so this is how the winding comes into the picture. So this is a reference flow, and why is the winding along the spanning tree branch gives you the height difference? Well, this is kind of what your question was. I don't know who it was though. Can't see the names, but so if you imagine you have a spanning tree branch, so you go along, go hit the branch, and then another way to think of computing the winding along the branch is that you kind of take this path. Why this path? Because this path is how your reference flow is defined. And again, if you go along the spanning tree branch, you do not cross any dimer. So it's basically going to be defined by the reference flow, which we chose. And the reference flow is related to the sum of the windings of these things. Okay. And if you want to be even more detailed, we see that this minus pi is going to cancel I mean, it's going to alternately cancel each other. And maybe I have been able to convince you that the winding is somehow related to the height function in this way, if we chose the reference flow properly. That's kind of all I wanted. Of course, there are some boundary cases and technical details and things like that, but hopefully you're convinced that this makes sense in some way. Okay, so now you can see that, I mean, one way it's kind of weird, because you have the dimer model, which has nothing to do with the embedding of the graph, but we're kind of relating the embedding of the graph in the reference flow. But in a sense, if you look at the fluctuations, of course, this reference flow is going to cancel, um, so that the height function is no way related to the embedding of the graph. But we are using this embedding and this winding and these topological things to compute the fluctuations. Okay, so overall, the summary is that we have this one-to-one connection with spanning trees. And if you have a uniform dimer model, that of course corresponds to a uniform spanning tree. And the third thing that we did is that the winding of uniform spanning tree, winding of dimer, sorry, height function of dimer, height change of dimer, is related to the winding of spanning tree. Okay, so now we ask, well, what can we say about the spanning tree? Okay, so now here is the good news, which comes from the work of Lola Schramm Werner, pioneered by Schramm in the beginning of this century, who proved that the spanning trees, the uniform spanning trees, has a very nice scaling limit. Okay, and there is a very explicit description of the branches of the scaling limit. It's not some abstract object which exists in some space. It's related to something called Schramm loaner evolution and things like that. So it's a very concrete object, as it turns out. Okay, so this is kind of what I'm going to explain next. But keep in mind that this is not going to be the end of the story, because as it will turn out, if you take the scaling limit of the spanning tree, um, the branches are going to be fractal objects. Okay, and in particular, if you take a point on the plane and you ask, well, what is the winding of my branches? Okay, first of all, as soon as it becomes fractal, the definition of winding that I gave you doesn't work, because it started with taking gamma prime of t. But if you have a fractal object, it kind of winds infinitely often at every scale. So that's we don't know how to make that immediately work. And also, even if you forget that, if you look at a point and say somehow you computed the winding, it's going to wind around infinitely often in both directions around every point. Okay. In particular, um, I mean, one way to maybe quantify how this thing behave. If you, let's say you take a point and you stop the branch as soon as it hits the ball of radius e to the minus t around a point. Okay. Um, it turns out that if you increase t and compute the winding of the spanning tree branches in this way, then the winding evolves like a Brownian motion. So as t goes to infinity, so e to the minus t, if it so if as t goes to infinity, e to the minus t goes to 0. So the winding sort of wildly fluctuates. I mean, the Brownian motion will fluctuate a lot. So therefore, it's not such a straightforward thing to get from the winding to the height function. Okay, and in hindsight, it's better not be so easy, because if it was something nice and simple, you wouldn't have gotten the Gaussian free field, because the Gaussian free field variance at a point really blows up. It's not a function. Okay, so what's the connection between spanning trees and random walks, and why did we need all these assumptions about random walks? If you remember the assumptions, well, spanning trees can be sampled very nicely using something called loop erased random walks. Okay, so very briefly, what this is, well, you do a simple random walk starting from a point. Okay, and as soon as you create a loop, you kind of erase it. Okay, so maybe you've heard this in one of in some other lectures. Um, so you erase it and then you go on, and then as soon as you create another loop, you erase it again. So you kind of chronologically keep erasing the loops um, until you have a domains until you hit the boundary. Okay, so you chronologically erase the loops. Okay, so you kind of, so this gives you a simple path. And what Wilson's algorithm, this is another remarkable result, at least even after I've worked with it for so long. It says that if you do this weird thing, it will give you a branch of a uniform spanning tree. And not only that, if you take any ordering of the vertices of your graph and start doing this loop erased random walk from these points. So let's say I've done this branch and I want to find the branch from this point. Well, I do start doing loop erased random walk. Okay, so I'm not showing the loops now, but at some point it will stop. Maybe it hits this branch. Okay, so then I stop. This gives me the second branch. Then maybe I hit the boundary. This gives me the third branch, fourth branch, and so on. Okay. So if I do it in any order from this collection of vertices, I get my uniform spanning tree. Okay. So it's a remarkable thing, but the point I want to use it, the way I want to use it, is that this gives a very, very concrete connection with random walks. Okay. Okay, now these random walks, these loop erased walks are going to converge to something called SLE. Now, okay, it has a very concrete definition.
Okay, got just one question. Where do you, I mean, is there any specific way you're sampling the points where you're going to start your loop erased random walk?
Yeah, it's a very good question. It's a very good question. It doesn't, I mean, in terms of the algorithm, it doesn't matter which order we pick. So we are completely free to choose any order. That's one of the magic of Wilson's algorithm. So we are going to choose it in an order we like to suit our purpose, depending on what we want to prove about these trees. Yeah. So that's one of the powerful things of Wilson's algorithm. Okay, and where does this loop erased walks converge if you let the mesh size of this thing goes to 0? Okay, so it converges to something called Schramm-Lohner evolution. Now I can spend 2 lectures on Schramm-Lohner evolution itself. It's a topic by itself. So I'm not going to do that, of course. But let me just point out simply that there is a very specific, stochastic differential equation, or it's a very simple equation. It's not something very complicated. It involves one Brownian motion here, which tells you how the conformal maps behave if you want to map out a certain branch. So if you want to find a conformal map from the disk minus this branch to the unit disk. Okay, So there is a way in which you can grow these curves with certain parameterization, such that if you look at this sequence of conformal maps, it satisfies a very, very nice and very concrete differential equation, which allows you to study them. And the thing is that these things are conformally invariant. Okay, so that's another thing that we're going to use a lot. And another thing that we're going to use a lot, that these things are independent in the sense that if you so it's going to be something like Brownian motion. If you so if you condition on the curve up to a certain point, the law of the remaining part, remaining branch. So imagine I'm growing a branch from 0. The law of the remaining branch is going to be the law of the UST branch in the domain which is slit by this curve. Okay. So if I slit by the red curve and I again ask what is the law of the branch started from 0 in this slit domain, this is the same law as the conditional path start once we have revealed this red part. Okay, so this is a very concrete object. Let me not just go in there, but the important thing is that the loop periods random walks are going to scale to a Schramm-Lohner evolution with a parameter 2. Okay, so the thing that we maybe should be content for now is that it's a concrete object, it's conformally invariant, and if you want, we can sample them directly in the continuum in a very, very nice fashion. So what's the way to do it? So in the continuum, you can ask, well, how do we grow a UST once we have taken the scaling limit using Schramm's result? Well, here is a very nice version of Wilson's algorithm in the continuum. So let's say I want to sample the branch from, let's say, this point. Okay. So what I'm going to do is I'm going to pick a point on the boundary of my domain according to the harmonic measure seen from this point. Okay. Well, what's the harmonic measure? Well, you basically look at the probability of a Brownian motion hitting a certain region started from this point. Okay, so this it's a probability measure on the boundary of this domain in R2. It's a very well-known thing. So you pick a point on the boundary according to the harmonic measure seen from this point. Okay, so let's say it's this red point, and then I'm simply going to draw an SLE2 started from this red point targeted at this black point. So remember, as I said, things are conformally invariant. So this equation gives you the definition of SLE targeted at the origin, but using conformal maps, you can define it in any domain. So here is a Wilson's algorithm in the continuum. You draw the branch from this red point to this black point. Then my domain is now slitted. So what I'm going to do is I'm going to pick a point on the boundary of the slitted domain now from my next point. Okay, so maybe it's some point on the boundary, but just to make my point, let's say this is a point here. Okay, so I picked one point on the slit according to the harmonic measure seen from my next point. Okay, and again I'm going to draw an SLE2 in my slit domain started from this targeted at this point, started from this red point, and then I'm going to continue in the same manner, and I can grow more and more of these branches, and things are going to get dense and dense. Okay, and this algorithm in the continuum, okay, so it's only going to give you any arbitrarily finite number of branches you can sample in this way. But in some sense, as maybe I will convince you perhaps in the next lecture, is that in some sense, if you draw a very large number of branches, that's enough to kind of understand the whole tree in some sense. Okay, so it's somehow finite dimensional with very high probability. That may be a very rough way to put it. Okay, now remember we were dealing with general graphs. So one thing I would like to quickly point out is that Lawler-Schramm-Werner proved things for the square lattice, but Yadin and Yehuda very nicely extended it to any general class of graphs where random walk converges to Brownian motion. Okay, so this is the setup. And the problem is that each branch kind of winds infinitely often in these two directions. And we kind of want to complete this picture that the spanning tree has winding given by the height function. and you get to continuum spanning tree using the results of Schramm. And then we want to say that the winding converges to the Gaussian free field, and the height function converges to the Gaussian free field as well by completing this commuting picture. Okay, so I think I'm kind of out of time, so maybe this is a good point to stop. And what I'll try to explain in the next lecture is how to make this program go through. In particular, there are several challenges for us. One is that how to define winding for fractal curves, how to do that. And the next challenge is how to make this picture commute, because remember, we also need to take care of the microscopic scale. So, if you prove some result about SLE2, that's not complete. That's not going to be enough, because in the microscopic scale, things could be bad and things might not converge at all. And then finally, what we want to do is we want to identify the limit using imaginary geometry, which I didn't have time to say anything about in this lecture. So, but maybe I'll stop at this point today and take questions if there are any.
Yeah, thank you, Gaurav, for very exciting lecture. Yeah, so we'll take questions for now, and yeah, people can just unmute themselves and ask questions.
Okay, I have a question. So this I really want to understand what the winding business was about. So I mean, for the Lozen's model, is the winding like, I mean, if you consider each of those cubes, then I mean, if you have a path, if you have a green path like you said, then it goes through certain staircases, right? So when you cross each edge in a cube, your I mean, the angle is changing, right? So you add up those angles. That's what the winding is, or what?
It's slightly more complicated than that. So let me get back to this slide. So remember, I told you this connection with spanning trees and dimers. Wait, so it's here on a very special class of graph called temper-Lane graphs. Now, for the Lozenge tiling, it's the hexagonal lattice, and the hexagonal lattice is not a temper-Lane graph. Okay, so if you look at a hexagon, well, you can see that every white vertex here, for example, is degree 4, whereas a white vertex on the hexagon is degree 3. So it's not a temper-Lane graph. So there is no such visual connection with a spanning tree. Now, the staircase thing that you were talking about is slightly different from the connection with spanning trees as per se. However, there is a way to connect dimers on the hexagonal lattice to spanning trees on certain graphs called T graphs, which I didn't explain, but it's a more complicated mapping. It's some kind of an almost linear mapping which twists, which makes these sort of these black triangles become sort of these lines, and these white triangles. So if you look at the dual, it will be um, right. So if you look at the dual graph, it will be triangular lattice. Okay, my drawing is not very good, but if you have these white triangles and you have these black triangles corresponding to black and white vertices, and there's a weird mapping, but not so weird when you look at it first. These things are going to map to some lines, and these white things are going to map to some triangles, and you're going to get some graph which looks somewhat like this. And the spanning tree on this weird graph and the winding of that somehow connects to the height function. Okay. Now, having said that, so it's more complicated on the hexagonal lattice, but you can do it. Now, if you try to do it on something weird like this picture, which I showed you, for example, this one. Then the trees are not going to be super nice near the boundary. So the boundary conditions are going to put some other conditioning on the trees. So the connection with winding and height functions is still there, but the trees are not too nice there for these boundary conditions. However, having said that, one of the things which I didn't tell you because of lack of time is that one of the main motivations of starting this work was to actually study lozenge tiling. Let me head to the picture that I want to, which is a bit later. On the graph where on lozenge tilings of actually this graph. So where you kind of have a linear slope. Okay, and it turns out that even this was complicated. Um, when you have like a constant slope for the lozenge heights, but you can map this thing to T graphs and study winding of T graphs. There, the T graphs are not too bad. I mean, not as bad as the hexagon boundary conditions, because you can see that the boundary conditions are kind of flat, not as weird as the hexagon where you kind of go in one direction and go in the other direction, which creates some twists. So that's why it's the spanning trees here are amenable, um, and that's why we could solve, for example, this particular problem by studying the spanning trees.
I see.
Okay.
Thank you.
Yeah. Any other questions?
Yeah, on the same note, I just had a clarification that I'd
Mhm.
like. So, when you're explaining the Temperley-Fisher correspondence, so at least visually, you just took any graph and drew its dual and then wired the leaves,
Yeah,
right? That's what you did.
yeah,
But
yeah.
now, when you're answering this question, you said that you were actually doing this for Temperley graphs. Is that right?
Yes. So the thing that I did with the dual thing is called it's called tempered lane graphs. Uh,
Okay,
they
so when
have
you merge and then wire them, that's called the Temperley graph.
yeah, yeah. That's yeah, exactly.
Okay, and so therefore you in his answer to the question you just said that the hexagonal picture won't be a temple length graph. That is, you cannot start out with a graph that draw its dual and wire the leaves to get a lozenge picture. Is that what you
Yes, yes,
meant?
exactly. So for example, the white vertices on a tempered lane graph will always have degree 4, but you can see on the hexagonal lattice it's not the
Right.
case. So at the discrete level, maybe sometimes you need to do some sort of specific thing to uh, change your things to something which is amenable to studying the spanning trees. Um, but I showed the Temperley picture because that's kind of most visual and maybe most direct to see. But there are other examples where you can connect to the spanning trees as well.
Right. And would it be possible to have a reference for the part where you essentially showed the connection between the difference in height function and the winding given by the spanning tree? Just would like to compute it and see. Yeah.
Yeah, yeah. So this was originally done in this paper of um, I think it's called Dimer Stylings and Trees by um, so this was the original thing, Dimer Stylings and Trees by Kenyon and Sheffield. I hope I'm not forgetting another author. I think it's just Kenyon and Sheffield. Correct me if I'm wrong, if there's someone in the audience. But this was only for straight lines and for simply connected domains. So in our paper with Nathaniel and Benoit, so you can look at it. It's on the archive. So it's called Dimers on Riemann surfaces. One. There is a section uh, winding and yeah, you can find the section number very easily. There's a list of content at the first page. It's called winding and spanning and height function or something like that, where we explain this connection in details, even when your graph is not straight lines um, and um, and yeah, to be honest, the proof here is kind of very short and maybe not very understandable if you don't see things as well as Kenyon and Sheffield. But here we kind of in this paper we kind of give a detailed proof of everything of how things go in Riemann surfaces and also in the simply connected case as well. Yeah, you can look at that.
Okay. Okay. Thanks. Yeah.
Thank you very much, Gourab. Very, very nice talk. Beautiful talk. Thank you.
Thank you for the invitation.